So last time we had defined homotopy strings, which then were going to give us the objects in the homotopy category, which is bounded of projective A modules bounded on the right and bounded in homology. And I said that these homotopy strings give a parameterization of the indecomposable objects there. So let me just briefly recall what a homotopy string is. So a homotopy string is a sequence of arrows and inverse arrows where we take form or inverses of the arrows, such that we can rewrite the sequence as a sequence of subwords where each sigma I is called a homotopy letter, and a homotopy letter is a sequence of direct arrows or a sequence of inverse arrows. And moreover, the sequence of inverse arrows should be a non-zero element in the algebra. And if we have two subsequent direct or inverse homotopy strings, then we would like their concatenation to be in the ideal. So composing them is 0. And then we define a homotopy band. That is a homotopy string such that the start vertex is the same as the end vertex. They shouldn't cancel each other, and the homotopy band should not be a power of another homotopy string, a proper power. And what is different from the string and band combinatorics for the module category is that we require a homotopy band to have the same number of direct and inverse letters. And when I say letters, I really mean inverse homotopy letters. Because we will see that homotopy letters correspond to maps which constitute the differentials, and somehow we want to end up in the same degree. That's the idea behind it if we have a homotopy band. Okay, then we did an example of homotopy strings. So we looked at these two algebras. So the type A3 tilde, and here, or maybe A2 tilde, I don't know. And here we have two homotopy strings. So we have a homotopy string given by AB, C inverse AB. This is one example. Or we have in this algebra actually a homotopy band, which is given by AB, C inverse. And this AB is a direct homotopy letter, and C inverse is an inverse. So we have the same number. And it's simply going around the quiver like this. If we now add a relation between the arrows A and B, then something changes. Namely, now AB no longer is a homotopy letter, but we can form a homotopy string by concatenating A with B with C inverse, similarly to the above. What changes now is that A is a homotopy letter, B is a homotopy letter, and then C inverse, and so on. And so then if we try to sort of go around and form a homotopy band, this does no longer work, simply because there are two direct homotopy letters and one inverse. And so this third condition is not fulfilled. Okay, in order to define a complex, we need a grading of the homotopy letters. And so this is the next definition. And so we take sigma equal to sigma 1 up to sigma n, a homotopy string or band. Then a grading mu given by mu 0 up to mu n on sigma is a sequence of integers such that mu 0 is just simply some chosen integer, and mu I plus 1 is defined recursively, namely it's mu I minus 1 if sigma I plus 1 is direct, and it's mu I plus 1 if sigma I plus 1 is inverse. Oops, verse. Okay, and this is for I between 0 and n minus 1. And I should say that this convention changed. I changed the convention from this last bit in the notes last time because I reversed all the maps, because I guess before I thought I might do left modules, but then I thought people might be more familiar with right modules. And if we do that, then somehow we have to change this convention. So just beware that in the first slide, it's a different convention. Okay, so now that we have the grading, we can really define a homotopy, a complex from a homotopy string or band. So we have sigma 1 up to sigma n, again a graded homotopy string now, with grading mu then we define a complex p sigma mu. So it goes from pk minus 1 to pk plus 1 with differential dk plus 1 by setting. So first we say what is the module in degree j. So we take projective indecomposables, namely for all those projective indecomposables where we have a grading mu I which is equal to j, for 0 less than I less than a, n, where pvi is the indecomposable projective at vertex vi. And what is that vertex? Well, v0 is the start of the homotopy string, and then vi is the target of the letter, of the homotopy letter sigma I. And we'll do an example in a minute, but we sort of group together everybody who in the homotopy string is graded in degree j, and that gives us the projective in degree j of the complex. And then each homotopy letter defines a morphism, namely, if we have a direct homotopy letter, we get a morphism from PVI to PVI minus 1. So this is if sigma I is direct. And we get a morphism from PVI minus 1 to PVI if sigma I is inverse. And from these, we can then define the differential. And yeah, okay, so similarly, we define a homotopy, a complex from a homotopy string. So the definition of a band complex is a combination of the above. Nation of the above and the definition of band modules. Namely, we have for each homotopy band, we have a whole family of indecomposables. So homotopy band gives rise to a 1 parameter family of band complexes. Okay, So before, okay, so then we also define a shift of the grading, and we define it in the following way, namely, if we have a homotopy string with a grading mu, then the homotopy string with the shifted grading is the graded homotopy string of the shifted complex, to be the graded. Of p sigma mu shifted by 1. Okay, and now it's the result by Beckett and Merklen. So they gave this construction. So Beckett and Merklen. They show that the string and band complexes arising from the string and band, homotopy strings and bands, parameterize the indecomposable objects in the bounded derived category of a Genta algebra. Okay, so let's see how that works. Oops. Okay, so how does that work? So example. So maybe we'll do again the same homotopy string that we had above. So we have 1, 2, and 3, A, B, and C. And we had the homotopy string A, B, C inverse. Then we now define a grading on it. So we can, for example, start at mu0 with n. Then we have a direct homotopy letter, so we go down, we have n-1, and we have an inverse homotopy letter, we go up. So once you fix the first one, all the others follow. And now we can construct the corresponding string complex. So we get the complex, which has in degree n-1. Maybe what is also helpful is to see where the string starts. So this is the vertex 1. Here we have the vertex 3. And here we have again the vertex 1. Okay, so in degree n-1, so this is Pn-1, we have everybody who sits in degree n-1, which is simply the projective at the vertex 3. So this is P3. And then in Pn, we have everybody who sits in degree 1, and there are 2 copies of P1. Okay, and in the differential here is simply given by the map that goes from P3 to P1 plus P1. Oops, there's a 1 missing. And it's given by the 2 homotopy letters. So we have a homotopy letter sigma 1 and sigma 2 here. So it's simply given by A and C. Okay, so what is really remarkable for these indecomposable objects, or these complexes in the derived category of a Genta algebra, is that they always unfold. So how does it unfold here? Well, we can write it really as a string. So we have P1 to P3, we have the map AB, and then we have the map C that goes here. And now you can really read it as A, B, C inverse. Or if you read, I mean, which corresponds exactly to the reverse order of these things. So you can really see the maps. And similarly, if you do it for the other algebra, which was 1, 2, 3, and we had A, B, and C, and then we had the homotopy string A, B, C inverse, then you will see that you get a complex which is given by P3, P2 plus P1, and then P1, where you have B, C, and A, and 0. And if you unfold this complex here, then it gives you P3, P2, P1, and P1. So you have B, C, A, and if we write the degrees in which the so if we start here at the beginning with maybe n again, then the n should be here, and we have n minus 1, n minus 2, and you can see that if you want to construct sort of a band, then you kind of have to be in the same degree at the beginning and end, like here. So this is a string complex, but we could construct a band complex. So let me write one down. For example, we could have, if the field is algebraically closed, something of the form AB plus lambda C into P1, and then this is a band complex, but of course there exists one for every indecomposable module over a polynomial ring. Okay, so these are the band complexes and string complexes. Yeah, maybe I leave for you to do, if you want, the sort of to construct complexes when you have an algebra of infinite global dimension. Then, for example, if we have A, B, and C, then we have an infinite homotopy string A, B, C, which just continues. And if this is 1, 2, and 3, then the corresponding string complex, which is then an infinite complex, is really the projective resolution of the simple at 1. Okay. Okay, so now we have all the tools in hand to describe this geometric model for the bounded derived category, which we will then see is actually a Fukaya category. So that follows from the work of Haiden, Katzarkov and Kontsevich, and Lekili and Polychuk. Excuse me for 1 second, please. Okay, so that's the second paragraph. So geometric model for the bounded derived category of a Genta algebra. Okay, so this is in joint work with Sebastian Opper and Pierre-Guy Plamondon. And maybe since this is the object of the whole lectures series, maybe I'll write down everything. So KQ over I is a Genta algebra. Then we have a ribbon graph associated to gamma I. Gamma A is the ribbon graph of A. And this ribbon graph sits in a surface SA and has dual graph gamma A star. And remember, I should have written this in red. I will consistently write this dual graph in red. Okay, so this is the data, the input data. Oh yeah, no, there's one thing missing. Namely, we define a set M bar, which is given by the set M. And if you think back about the construction of the ribbon graph, these are the black vertices. So they're the maximal path, and then some idempotents of sinc sources and some other vertices. And to this, we add all the red punctures. So not all vertices of the dual ribbon graph, but just the punctures. And with this, we can then say that SA, the dual ribbon graph, gamma A star, and the set M bar gives the geometric model geometric model of the bounded derived category of the Genta algebra. And what do I mean by this? Well, it describes the indecomposable objects and dimorphisms between them. So the first is we're going to describe the objects. And I have to say that this geometric model is really based on the work of many, many people. And at each step, I will tell you whose work it is based on. So the objects, the indecomposable objects, in this bounded derived category, well, we have the complete description by Beckert and Merklin. And using that, we can show that they're in bijection with graded curves, gamma F, where gamma is a homotopy class, of curves of the form, and I will draw the curves. Okay, so they can be curves connecting two marked points on the boundary. That's one option. They can be a curve going from a boundary to a red puncture, but if this happens, then the curve is necessarily going to wrap around this puncture in the clockwise direction, like so. And because it's always in the clockwise direction, we can write it as by sort of abuse of notation in this way here. And of course, we don't really view the red point as a puncture, but maybe as an endpoint compactification of a puncture, so that we can asymptotically approach it. And then there's also the possibility that the curve goes from one puncture to another. So it wraps clockwise here, and then again clockwise here. So again, we denote this by drawing just a curve like this, connecting the two punctures. And finally, there's also going to be certain closed curves. Oh, curves, maybe write it here. Okay, so curves like this. And if we have the curve, then it comes with an indecomposable local system, which is just something like the indecomposable modules over polynomial ring in one variable. Okay, so I'll say in a moment which closed curves appear. Basically, if you have seen James Pascalev's lectures, he said that not all Lagrangians are sort of in these Fukaya categories, but they have to have winding number 0. And this is precisely what we find again here. And the winding number we here define is a combinatorial one, and it comes from the grading. So what is this F? So remember the indecomposables are in bijection with graded curves. So we have to say what the grading is. So F is the grading, F is the grading on gamma given by, it's a map from the intersection of the curve with that dual ribbon graph on the surface. So the right ribbon graph is also embedded on the surface. It gives a dissection of the surface, and we count the intersections and order them and in the orientation of the curve. and we define this map F as follows. So suppose our curve crosses the red ribbon graph in this way. So here's our curve gamma. It will have intersections X, Y, and Z. And remember, the surface is dissected into red polygons, and it is such that each red polygon has exactly one boundary component with a black marked point. And let's assume for a moment that the configuration is in this way. Then if we go in the direction of the curve from one red crossing to the next, if that marked point is on the left, we add 1 to our grading, and if that marked point is on the right, we subtract 1 from our grading. So we get the rule that f of x plus 1 is f of y, and that's the same as f of z plus 1. So somehow, if we have a grading of n here, then we get n plus 1 here, and we get n here. And so we can then, if we have a curve, we can go along the curve, just going from red intersection with the dual ribbon graph to the next one, and so on. And if we do that for the whole curve, we get a winding number, or we get an integer for the curve. We can do that both for open and closed curves. And so therefore, we get a sort of combinatorial winding number. W gamma. And this winding number encodes both the grading of the complex, of the indecomposable complex, and also the shift functor. Well, or you can sort of realize the shift functor in this way, I should say, maybe. Okay, and now we can say which closed curves are actually in the surface, namely those closed curves with winding numbers 0. And we'll see in the next example that this is really the same. The winding number is really counting direct and inverse homotopy letters. Okay, so let's maybe do the example, okay, I wanted to do this example. Let me see if I can maybe copy and shrink it. No. Okay. Okay, so it's small, but hopefully still readable. Can you still read this? Is it too small? Maybe like this? Better? Okay. Okay, right. Okay, so we have two Genta algebras, and let me quickly draw the surface. The construction on the surface is in the notes that I think Daniel has put in the chat. But let's compare the two situations. Remember, on one side, on this side here, we had a homotopy band, and here we didn't, and we can see now why. Okay, so what does the surface look like? Well, it's an annulus. So I need a second circle in here. In both cases, we have a mark point, bright mark points on the boundary. But remember, for our geometric model, we only need the red ribbon graph. We don't really need the black one. We just need the vertices of the black graph. Okay, so we have this here, and this corresponds to 1, 2, and 3, to the vertices in the quiver. And now I would like to draw this homotopy string here. So this is A, B, C inverse. And maybe before I do that, it might be helpful to also draw the arrows. So we have A, we have B, and then we have C like so. Okay, and now the homotopy string. Okay, so first we do A and B. So we start here. We do A, B, then we do C inverse, and we connect to the next possible black mark point. Okay, so where are our homotopy letters? So the homotopy letter AB, which is sigma 1, goes from this intersection of the green curve with the red curve to this intersection here. So this corresponds to sigma 1, which is AB. So here AB. And then C inverse goes from the next intersection. So basically you decompose your curve into these segments in the red polygons. Okay, and then you connect to the next mark point. So you connect here and here. Okay, then if we quickly draw the model for the other one, we get this, this, and this, and then we get this graph here, and we get the homotopy string, which is up here. So let's call this maybe gamma. Then we get a similar curve, very similar, so nothing much changes. Okay, now what about the homotopy band that we have here? Of course we can, yeah, we only have the letter, we can't really see the complex because it's an infinite family of things. But what does that look like? Well, it's given also by A, B, and C inverse. But this time it's a closed curve, so it goes the same as this one, and then it closes like this. And now we want to count the winding number. So what we do is, if you remember, we had this rule that if the mark point is on the left, we go up, and if it's on the right, we go down. So let's do our curve. So if we go here, the mark point is on the right, and so we go +1. Then the mark point, if we go here, is the mark point is here, it's on the left. So the winding number of delta is, was it -1 +1? I can't remember the left, right. Okay, let's see. Okay, so if it's on the left, it goes up. So here it starts with the right, so it's +1 -1, and we get winding number 0. If we now look at the closed curve over here, well, then if you count from here to here, the mark point is on the right, so it's now it's -1. From here to here, it's also on the right, so it's -2. And from here to here, the mark point is on the left, so it's -2 +1. So we get winding number of that blue curve, which is equal to -1. And so this means that here delta is not in the derived category. Of course, it should be the whole complex, whereas here delta is in the derived category. Okay, so this is the construction of the objects. Now, what about the maps? So we describe a basis of the Hom space of two indecomposable. So instead of writing them as complexes of projectives by abuse of notation, I take the graded curve and identify it. And so I write it in this way. And here, in order to describe the map, we use work by Arnesen, Laking, and Puxtello, where they describe the spaces in terms of homotopy strings and bands. Okay, and so what do we find? Well, we find that this basis is in bijection with well-graded, oriented intersections of the curves gamma and delta. Okay, so this is almost true. It's not quite true because it's a bijection in all cases except if gamma is equal to delta and they're both a simple closed curve. And if the grading f is equal to the grading g for some reason, then the identity map of that band complex cannot be seen as an intersection. And similarly, if we have a band, an endomorphism of a band, or to its shift, then there we have sort of this map which is given by the Auslander-Reiten triangle. Can also not be seen as a graded intersections, but otherwise all maps are there. And I find that actually quite puzzling because we will see in a moment that these are really Fukaya categories, and Fukaya categories do have the simple closed curves. And so I don't really understand why these two maps are not there, but somehow the algebra says they're not. Okay, so what is a well-graded intersection? Well, okay, so we have our curves gamma and delta, and they might intersect at some point Q. And Q can be on the boundary, it can be in the interior of the surface, or it can also be at a red puncture. Okay, and then we look at the next possible intersection of our curves with the dual ribbon graph. So this is part of this dual ribbon graph, and we call this y and we call this x. Then somehow well-graded means in almost all cases that we have that the grading of gamma, so f of x, should be equal to the grading of delta at y, so g of y. So the grading here and here, they should coincide. Okay, but we can be a little bit more precise. So can be more precise. So let's fix gamma f. And let's look how the different intersections give rise to maps. So the first one is if Q, so this intersection is in the boundary, then there is a grading G on the curve delta such that either we have a map from P gamma F to P delta G, and this happens exactly if in the surface we have gamma and then delta is sort of in the counterclockwise direction from gamma, and I should maybe also have drawn this here, so our maps always go counterclockwise, or if we have the other thing, namely that in our boundary we have first delta and then gamma, well then of course we get a map in the other direction. Okay, so this is if this intersection is in the boundary. Oh, forget. If the intersection is in the interior, then again there exists a grading G on delta such that we have two maps. Namely, we have one map from gamma F to P delta G. But of course, if you look here, then we can also have an intersection here, and then there should also be some other map psi over here. And this is precisely what we then find. namely the same grading if we shift it. Oh, well, not, well, if we, well, either shift it or shift the other one, we get a map here. Okay, so we get two maps. And then if we have an intersection which is at a puncture, so what does it mean, an intersection at the puncture? So that means that the curves wrap around in the clockwise orientation along this puncture, and so that they approach it asymptotically. And then we get an infinite family of maps. So if Q is in the puncture, then there exists a grading G on delta such that there are two infinite families of maps. Namely, we get a map from P gamma F to P delta G, and we shift it by ML, and I will say what ML is in a moment. And we also get a map from P delta G to P gamma F, where we have ML plus 1. So it's similar to an intersection at the interior. So what are the M and L? So M is simply a positive integer, and L is the valency of Q as a vertex of the dual ribbon graph. So remember, the red punctures are actually vertices of the dual ribbon graph, and so L is simply the number of edges at that vertex of the dual ribbon graph. Okay, so maybe an example for maps for this. Let's do a simple one. Let's take the A3 quiver, 1 to 2 to 3, A and B. Then it's fairly easy to construct the surface. Here it is. It has 4 marked points, 1, 2, 3, 4. Therefore, it has 4 red marked points. And the dual ribbon graph looks like this. We have 1, 2, and 3. Okay, and now let's take this object here. This corresponds to the projective P2. So somehow, oh yeah, okay. And let's take this object here. This corresponds to the projective P3 to P1, which is given by the homotopy string AB. And then we have two intersections. So let's call this here gamma, and let's call this delta. Then let's maybe first do phi, because it's an intersection in the interior. So if we fix gamma and F, so gamma is P2. So here we have P2. We fix it with the grading, so we say it's in degree n. And then we know there exists a grading here such that we have a map, and indeed the grading should be such that this is in degree n and this is in degree n minus 1. And so this is the map phi, which is of course given by A. And then we have a map psi here, which is simply the map, sorry, you can check, which goes from the complex P3 to P1. And now we shift P2 and we have a map here. And this is the map psi, which is now given by B. And somehow you can really see that because the B sits here and A sits here, and remember that we reverse the direction. So really you can see the maps as, oh sorry, I drew them in the wrong way around. Apologies. Okay. So this goes from 2 to 3, that's B, and then of course from 1 to 2, and that's A. Okay, so these are our maps. Then what else can we see? Well, so let's go back to this result with Opper and Plamondon. We know that the indecomposables in KB Proche are exactly the curves that connect boundary components and the closed curves with the local system. And of course, we know that in this category here, we have Auslander-Reiten triangles. So, well, maybe two things are important. So recall that KB Proche A is isomorphic to the whole of the derived category if the global dimension of the algebra is finite. And the second thing is that KB Proche A has Auslander-Reiten triangles. Okay, so now we can see the Auslander-Reiten translate and also the Auslander-Reiten triangles on the surface. How is that? Well, for that we use work by Bobinski, Arneson, Laking, and Puxtello. Okay, and that gives us the following, namely, now of course we have to only consider curves between boundary components. If we have a closed curve, then it's own Auslander-Reiten translate. But if we have a curve gamma in this way, then tau inverse is simply obtained by rotating in the clockwise direction on the boundary. So tau inverse is this, so tau is the anti-clockwise rotation. And actually we get the whole of the Auslander-Reiten triangle because we get the Auslander-Reiten triangle by just rotating one endpoint. So if you're familiar with how it looks in the cluster, surface cluster category, this is exactly the same. And then we get the corresponding AR triangle, which is here gamma with some grading F. Then here we have maybe alpha 1 and alpha 2. And then there exists grading F1 on alpha 1 and F2 on alpha 2, such that we obtain here tau inverse of gamma F, an Auslander-Reiten triangle. Okay, this can be generalized by using two mapping cones. So in general, between indecomposables. So this is triangles in the bounded derived category from mapping cones of basis morphisms in number 2 above. Okay, so how does that work? Well, it corresponds to geometrically resolving the crossing, and that's also very similar to the cluster category. So we have gamma and delta, and I should maybe say also before I forget that this is using joint work with Ilke Cianacci and David Puxtello. Okay, and so what we find is that if we have two curves, gamma and delta, then there is an extension if these curves cross well, and of course then we have a map phi as well, but and somehow this is given by the mapping cone of phi, and we then resolve the crossing, so we get two maps, alpha 1 and alpha 2, where we just follow gamma up to the intersection, and at the intersection we switch and follow delta, and this is alpha 2, and then we get the following triangle. So we have gamma f, we get a map phi to the curve delta with some grading g, and then we have by construction the mapping cone, and then this completes to a triangle, so we can always do this. The shift, and this mapping cone we show is isomorphic. So this is shown, well, based on this work with Giannacci and Puxtello, that this is alpha 1 f1 plus alpha 2 f2, and this generalizes really what we have seen for the Ausländerweiten triangles. Okay, so maybe we should do one example of this so that you can convince yourself. I'm going to try and do it up here. Okay, so maybe which map I'm going to do psi. So let's maybe keep, oh, this is mislabeled. This should be psi, I think. Okay, and let's get rid of phi. And let's move psi out of the way. Okay, so what do we have? Okay, so we have the map psi, which is here. And now somehow things we should get, if we resolve the crossing, we should get this curve and this curve. Well, okay, so the theorem says that we get it. So what does it say? It says that we have a map from delta G, maybe shifted by -1, and then we have psi -1 gamma f. We take the mapping cone, then we get this curve alpha 1, alpha 2. So we have alpha 1 f1 plus alpha 2 f2, and then we go on to delta G. And if you write it out in terms of complexes, then you can actually see the maps. So here you get, of course, P3 to P1 shifted by -1. Then you get our map psi -1, which is given simply by B. Then we have the complex P2 concentrated in degree 0. Then we have P1 plus P3 to P2, which corresponds to alpha 1 and alpha 2. And then we have P3 to P1 here. And in fact, this is an AR triangle in the bounded derived category of the A3 quiver. Okay, so we can see that. Right. Okay, so this is basically almost everything we know about the geometric model. There's a few other things which I'm going to talk about next time, namely the Gentile algebra also encodes a line field. We can also see the Avella-Alaminos and Geiss invariant on the surface. But what I would like to do first today, at least introduce it a little bit and then continue next time, is the relation of this with the partially wrapped Fukaya categories of surfaces with stop. So this is then maybe section 3, relation to partially wrapped Fukaya categories of surfaces with stops. Okay, so so these partially wrapped Fukaya categories were introduced by Denny Oru. Namely, he gave a construction of partially wrapped Fukaya categories of symmetric products of Riemann surfaces with stops. And I believe that Gustavo Hasso in his talk is going to give an algebraic description of these these partially wrapped Fukaya categories. Okay, and then Haiden, Katzarkov and Kontsevich give an explicit combinatorial construction of the partially wrapped Fukaya category of a Riemann surface, so a symmetric product only with one component in the product, Riemann surface with stops. And I'm going to say something more detailed about this construction next time, enough so that you can really see how it relates to the bounded derived category of Genta algebras. But I would like to mention here as well. So basically, what they do, they construct this Fukaya category and then show that it's really equivalent, derived equivalent to a graded, a homologically smooth graded Genta algebra with zero differential. Okay, but then Likely and Polychuk give an inverse construction to this. Likely and Polychuk. And they do that in a paper that appeared at the same time, roughly, as the paper with Sebastian and Opper and Pierre-Guy Plamondon. And so what do? They give a converse construction to the Haiden, Katzarkov, Kontsevich construction, i.e. starting from homologically smooth, which for Genta algebra simply means a finite global dimension graded Genta algebra. Give a construction of the partially wrapped Fukaya category of a surface with stops. And so this construction by Haiden, Katzarkov and Kontsevich a priori is more of a topological one, but they have a remark in their paper, and according to the experts, so that remark says that basically if you follow a proof similar to the proof of Abu Zaid for the case when you don't have any markings or stops on the boundary, then you actually get the symplectic construction that can apparently also be gotten from a paper by Ekholm and Likely, but I don't know. But be it as it may, next time we will look at this in more detail and compare it to the geometric model, and then also look at line fields and derived invariants. Thank you.
Yeah, thank you, Sibylle, for the nice talk. And are there any questions? Feel free to unmute yourself or ask in the chat.
Okay, so Gustavo says that they only describe the case of how to describe the singularity category. So the singularity category has been described by Martin Kalk and for Genta algebras, and it corresponds and basically it corresponds to the red. So it's given by basically orbits of sort of semi-simple parts, and each semi-simple part corresponds to a red puncture, and the order of the orbit is given by the valency of the red puncture as a vertex of the dual ribbon graph. So you get a complete description of the singularity category on the surface.
Any other question? Yeah, so maybe I have a question, which is when you described, when you mentioned a description of the AR translation, and I think Brusley and Chang and Brusley and Q have a similar result, but for the cluster category.
Yeah, that's right, exactly. So it works exactly as in the cluster category.
Yeah,
they also get the description in terms of rotation
right.
To the next mark point in the boundary.
Right. So my question is maybe it's a silly question, but how well is it understood, you know, the relation between the derived category and the cluster category in that case? Like, is it understood or?
I guess the only case when it's really understood, or at least maybe some experts can say something else, is in the hereditary case. So if you have a hereditary Genta algebra, then I suppose by the construction of the cluster category, you can sort of relate it. Of course, you can easily relate the surface model, and there are many indecomposables which are represented by the same curves, but the cluster category has some more curves. I mean, it's a little bit different, right? Because you get, yeah, I think you have more curves for some reason.
Okay, thank you. Are there any other questions or comments? If not, let's thank Sibylle again. And let's meet again in